Okay, hello everyone and welcome to today's webinar, Accelerating the IoT Edge with PSoC 6.3 BLE and Machine Learning. We are joined by Seshadri Paravastu, Product Marketing Infineon, and Joshua Buck, Solutions Engineering at Edge Impulse. If you have any questions during today's webinar, please ask these in the Q&A box and we will answer as many as possible. And with that, over to you.
Hello everybody, welcome. I'm excited to be here in front of you as a member of the product marketing team for Bluetooth product line at Infineon. And today I'll be sharing with you details about our PSoC 63 Bluetooth LE device and how this can be used as an edge device for typical machine learning IoT applications. So the agenda for today is, first I'll spend about 15 minutes or so and give you an overview of the PSoC 63 LE MCU for edge devices, specifically for AI ML applications, how this part fits in the market space, and also point out several applications that could use AI ML. And I will point out a commercially deployed product where this PSoC 63 device is currently used. Then Josh, who is here with us from Edge Impulse, will then give us an overview of the Edge Impulse Studio, talk about how to get started with the training ML models, download the firmware onto the PSoC 63 Bluetooth LE MCU kit, and then deploy it to ingest data from the sensors and train the models, and finally create inferences to give you a demonstration of the system. So after the session, you'll walk away with a good understanding of how we can use the hardware kits from Infineon and machine learning models from Edge Impulse to create interesting applications rapidly. Lastly, we'll try and reserve some time to answer any questions you might have. And in the meantime, if you have questions, you can type them away, like Louise pointed out, and Ashok, who is here, will try to answer them. So let's dive in. Infineon has been a leader in the wireless connectivity for more than 2 decades, and since coming up with the first CMOS Bluetooth radio in early 2000s. Since then, industry kept evolving and we keep making progress in the space. This progress that I'm referring to transcends both innovation and a vision for a future where wireless connectivity crosses the boundaries and becomes ubiquitous. As you can see from this chart, we keep pushing the envelope of what's possible and help develop innovative solutions based on these technologies. This chart is also a short reflection of the path that the pioneering breakthroughs have helped shape the course of the wireless connectivity. And when we fast forward to 2003 and into the future, when you think about various technology trends within this IoT space, you realize this is the age of edge computing and internet-connected devices. Recently, I was reading the State of IoT report by IoT Analytics from spring of this year, where they've identified a number of global active IoT connections at over 14 billion units today. And by the way, this number doesn't quite include the sensors and the actuators that is connected to each of those active connections. That 14 billion number in terms of IoT connections is projected to grow at a very healthy 16% compound annual growth rate to about 30 billion devices by 2027. So the trend here is there is a strong push to move compute performance to the edge, and wireless connectivity is continuing to play a major trend, a major role in this trend. When you think about proliferation of smart devices at the edge, by that I mean the devices that are acquiring data from the sensors, processing the raw data to make sense out of it, and also drawing meaningful inferences using machine learning and making intelligent decisions. So these tiny devices need a fair amount of processing power on them. And at the same time, many of these edge devices also tend to operate on coin cell batteries and extremely sensitive to power that they consume. Oftentimes, these are quite complex in terms of other things they need to connect to and to exchange data with them, right? So they need to also fit in tight spaces, and oftentimes they also operate in tough environments. So the form factor, the hardware design complexity are all important factors in this. Many of these applications also are increasingly seeking to add sophisticated human-machine interfaces like touchscreen capabilities or AI processing capabilities like voice analytics, for example, right? Infineon is committed to enabling you to develop these AI/ML models on your own or use predefined models from us or from partners like Edge Impulse to complement the hardware offerings that we have. Speaking of hardware, another interesting trend that comes to my mind, especially within the high-performance designs and high-performance MCU class of devices, is the number of cores that is supported in hardware. If you just go back a couple of years, the number of single-core processors happen to be about 70% or more in the new designs. That is forecast to drop to under 50% in a year or so. So this trend for multiple cores is increasing and is bringing enhancement, right, to various areas like watchdog functionality, adding user interface, using, or even just to isolate multiple threads that are being used within the same chip. We all saw this trend taking over in the application processors and the microprocessor space. Now it is a strong emerging trend within the MCU space as well. So as I pointed out earlier, AI and machine learning are being integrated into IoT devices and platforms to improve their functionality and efficiency. Infineon's P63 BLE MCU, it is designed with these in mind for edge IoT applications. It is designed to address the IoT market with the needs of long battery life, flexible interfacing for data connectivity, Bluetooth LE support, advanced security, right, which are all needed for the edge devices. The PSoC 63 BLE enables battery-powered applications to last longer versus their typical power-hungry application-specific counterparts with ultra-low power consumption features. At the same time, it also gives you additional faster processing capabilities compared to typical low-end microcontrollers. Probably PSoC 63 BLE is the only 150 megahertz MCU class device that is out there. So now let's dive a little deeper into specific features that PSoC 63 BLE offers. The PSoC 63 Bluetooth LE is based on the PSoC 6 MCU platform. And this is a combination of high performance microcontroller with low power flash technology, digital programmable logic for flexibility, high performance analog to digital conversion, other standard communication and timing peripherals. The PSoC 63 product line provides wireless connectivity with Bluetooth LE 5.2 compliance. It's on a 40 nanometer node with integrated hardware-based security features. It's a dual core with 150 megahertz ARM Cortex-4 M4 core with a floating point unit, and also a 100 megahertz ARM Cortex-M0 core. The feature-rich MCU peripherals, right, they all translate into reduced system BOM for you in your typical IoT applications. And it's also got a 288 kilobyte RAM for feature-rich wearable and sensor fusion use cases. It's got programmable analog and digital subsystems that allow you to hang a variety of sensors. And with this device, you can also precision manage your performance and power consumption. It is spec'd at 22 microamps per megahertz in active power mode. And it's got a 7 microamp deep sleep current with 64 KB RAM retention. So your hardware designs can support a long battery life. This also provides wireless connectivity with Bluetooth LE, right? With wireless connectivity also comes the need for security. It's got a crypto block. It's capable of supporting RSA, SHA, AES algorithms. This means a fully trusted execution unit that supports over-the-air updates as well as secure data transmission, allows you for data storage. So the question that's on your minds probably is, how do you get started with this device? So you can get started easily with the PSoC 63 BLE Pioneer Kit, which I show on the left here. And this has a 2.7-inch e-ink display shield on board with 3 sensors. It's got a onboard inertial motion sensor unit. It's got a digital microphone and a thermistor. On the main board is the BLE antenna and the headers that are compatible with Arduino Uno Shield boards. It's got a 512 megabyte QSBI NOR flash and proximity sensors. So I've included a few links for you here to get started with. Here is a link to the firmware. Here is a link to some Modus Toolbox examples that will allow you to get started with. And this is the recommended kit with Edge Impulse Studio support as well. Josh here will go over the details in just a little bit. Next to that is our CYHC Proto 063 BLE kit, And this kit is designed in a snap-away form factor, allowing you to separate the kit prog, which has an onboard programmer and debugger, from the main target board, and you can use it independently. I've included some examples of AI-powered smart ball implementation, which we have done. In this implementation, we actually embed this board into a foam ball, and via Bluetooth, you can see the inertial motion sensor gather the data, do its inferencing work, and then it'll render the results on a mobile phone. You can watch that. Now, let's look at what sort of AI ML applications are possible with this device. With an onboard digital mic, right, you can think about voice command applications. One of these could be like a key spotting to identify wake words in an audio stream. A typical key spotting, keyword spotting system will deal with a variety of speech features, right? Acoustic modeling, post-processing. You have to ensure robustness of the system. Sometimes you have to train models with rather large data sets. And many facets of this are embedded into the Edge Impulse Studio, and Josh will give us an overview of how to collect data from digital mic and classify them, how to train the ML model, and then deploy it onto the PSoC 63 BLE Pioneer Kit. Finally, you can also get creative and render those results on a Bluetooth, via Bluetooth using a mobile app. The next application is you can think about continuous motion recognition applications. For example, a gesture recognition model where you're collecting data from the IMU sensor. You can build a classification model by training and labeling different motions, maybe up and down and wave and idle type of motions, or other motions that you can think about, and then deploy the ML model onto the PSoC 63 BLE Pioneer Kit. Josh will go over how to do this in the Edge Impulse Studio environment. And again, there are a lot of powerful features in this, right? So you can use creating impulse vectors and using spectral analysis to identify anomalies. They give you visual representation of confusion matrices. And finally, you can download the model to the PSoC 63 BLE kit. This will allow the model to run without internet connection, and then you can run all this with minimum power consumption. Edge Impulse also packages all this neatly along with the signal processing code and neural network weights, right, as well as classification code into a single C++ library, and then you can include this into your embedded software. And of course, with the Bluetooth, based on GAT profile, right, or Bluetooth generic attribute profile, you can render those results onto a mobile app as an example. So when you think about market applications for something like this, right, with the market for elderly care and medical devices that are in great demand, use cases like fall detection, for instance, right, when an elderly person says, hey, ouch, or help, or other keywords, you can passively listen for these words and then issue call alerts, either for a family member or a nurse, as an example. And these are some of the applications in the wearable segment, like a wearable band or a smart ring. And here is a market ready, in other words, commercially available device that we are a part of today. And when you think of developing devices like this, typical requirements that you tend to encounter is the device needs to last maybe a week or a bit more, right, on the battery before you get to charge it again. It needs to continuously process data, right, for long periods of time. And then you can also imagine the form factor, right, for something that needs to go around a finger. It needs to store data, right, in between synchronizations. So you need to have on-chip flash and store the information on there. And then to add it all together, the end user experience needs to be outstanding, right? So we bring all this to the table with our PSoC 63 BLE device. Now, here are a few other focus areas that you can think about for edge applications, right, with the PSoC 63 BLE, either in home automation or human-machine interface, using wearables, battery-powered applications, portable medical applications. So I've listed some of the generic requirements that these type of segments typically have, and you can go through them at your leisure, right? And of course, I do realize every application might have their unique nuances. So now you can get started easily with developing and deploying powerful solutions for a range of ML applications like we talked about today. I leave the link here for you to go online and download the user manual and purchase the kit. So further, there'll be a deep down technical discussion also with Ashok and Josh further down the road, so stay tuned for that as well. And with that, I turn it over to you, Josh.
Thank you, Seshadri. The product is very powerful, the PSoC 63, with a lot that we can do for both on the ML side and the BLE side. Today, I'm going to give a presentation on how to use it with Edge Impulse and to develop, quickly get started with the product in the platform for machine learning. First, allow me to present a few slides about Edge Impulse and give an overview about what you need to do for model development. And then I'll do a demonstration of actually collecting data and deploying back onto the device. Edge Impulse is a fully integrated ML platform. So that's to say that we can take, not only do data collection and data organization and data labeling, but model training and model development, testing applications, and then finally edge device deployment or embedded device deployment like on the PSoC 63 and PSoC 62 lines from Infineon. Our business model is royalty free. That is to say, we do not charge a per device deployment. We're a SaaS company. We have two basically tiers of accounts. We have a free tier that's limited to 20-minute job times. For example, if you need to train a model that takes compute power, you have a limited time of about 20 minutes on the free account. And after that, it's an enterprise paid account to get more training time, faster performance for training, etc. But at the end of the day, your IP is your IP. So your models that you develop, your data that you collect is able to be extricated from the platform so that you can continue development on your own. But ideally, you find a benefit in Edge Impulse to continue your model development journey. We also highly espouse open source. So a lot of our DSP and model training code is online for you to download via GitHub or even in the platform itself. If you're not familiar with ML applications, this is a very broad overview of what you need to do to get ML running on a device. We'll be going through each one of these sections individually, but in general, you need to have some sort of ability to collect data. You might go grab a data set that exists out there. Edge Impulse makes this very easy. Or also you need to collect on device. So I'll be doing that today with the PSoC 63. And then you might need to develop it and get data from your device in situ. So maybe not a dev board, but an actual final end deployment. You can do that again with the Edge Impulse firmware. Once you have data for some sort of model or ML application, you need to design and train the model itself. So we have tools and algorithms and training code that are low code to no code ways to get a model developed. And then you need to be able to test that model before you even go back on the device to get some sort of sense of performance and benchmarking. And then we also make it very easy. Edge Impulse makes it very easy to deploy back onto the device in a low to no code fashion. So there's different deployment options as well. We'll go through each of these individually, and then of course I'll demonstrate it as well. So for data collection, we offer the ability for ML teams to basically collect data at scale. So you can do it with just one devices or many devices can connect to the platform. You can take it, data can come from anywhere. For today, I'll be demonstrating like accelerometer data, but you could easily take accelerometer data from your phone or from another device and then use it on different devices so that data is can translate well. There are auto labeling tools. There's ways to split and crop samples. We even have visual tools to do to track objects between picture frames so that you can label data quickly. And of course, you can bring in data sets as well. We want to make sure that your data is secure, so we are SOC 2 compliant. We also have secure data portals, so you can sign data with certain keys to make sure they're encrypted. You can even bring them in from Amazon S3 buckets as well if you have large amounts of data that you're continuously working with. This here is a screenshot of the Impulse design. An Impulse is really how you collect the data from the device, and maybe accelerometer or a microphone or a camera, what kind of DSP you're going to do on that data before you feed it to the model, and then the model itself and what kind of inferencing you're going to do. All our code is DSP codes online in our GitHub repo, so you can again work with it. There's really two components for DSP code. There's a Python code that you run in the cloud for model training, model development, and of course there's the stuff that you run on the device itself, exports to C and C++. During model testing and model after you designed your model, we want to make sure that you're aware of what hardware you're programming against, right? So we give inferencing and performance benchmarks across a wide range of supported products. And we want to make sure that you're able to see that across the pipeline. So that's to say, how long does it take to grab the data? How long is the DSP going to run? How long is the inferencing going to run? And then there's ways to tune and post-process your data. So for example, here on this picture, we have keyword spotting. And what we're able to do is take your data sets, your test and training data sets, superimpose them upon a noise background, and then tell you, what are your false activation rates or your false positives. That's just a way to give yourself more confidence before you go out into the field and try things out. Of course, the cloud environment is not the field, right? And so we try to make it very easy to deploy onto the device so you can see real world performance as well. We have a large ecosystem of silicon partners. Infineon's one of our premier partners, and we make sure that our models run very well on these devices. With that, I'm going to go and demonstrate how to get started with an Edge Impulse project. It really is as simple as heading to edgeimpulse.com, creating an account. We just need an email, ideally your work email, and your name. That's it. You get started with the developer access, which has a limitation of job time and the amount of size of the data that you can use. All the tutorial projects that we have today can be run on the free account with no questions asked. So I'm going to log into an account, and I'm going to go ahead and create a new project. Today, I'm going to call it the PSoC 63. And here is an Edge Impulse project. This is the primary environment from which you're going to collect data and then develop your model. If you remember on the slideshow, we had discussed about data collection, design, test, and deployment. Those concepts are represented here on the left-hand side on these tabs. So we have the ability to look at our data here. Once we add it, we will be able to create an impulse, and it's going to say, of course, that we don't have data, but we'll design the model, and then eventually we'll deploy it. So let's talk about where we can get data from. Here you can connect a device. This QR code is live. You can actually start putting camera image data or microphone data or accelerometer data. But instead, I'm going to go ahead and connect up the PSoC 63. So we have a documentation page. It outlines what you need to do to get started with the device in Edge Impulse. You just need a few prerequisites. You need to install the side programmer. This is how you get the Edge Impulse firmware onto the device. And then you need the Edge Impulse CLI. What the CLI does is it connects a device that may not have a network connection naturally, like the PSoC 63, since we haven't integrated any network connectivity other than BLE at the moment. And so it connects via the serial cable to your computer, and then the computer then does the network relay to get data into Edge Impulse. I have already uploaded firmware to the device. I'm going to do another firmware update later, so I'll demonstrate how to flash it in a later section. It's the same thing in the interest of time. But I can connect the device to the project, and I've also installed Edge Impulse CLI to the machine, so there's instructions for that as well. Since I have a large number of projects that I have access to, one way that's easy for me to find a correct project that I need to connect to is go to the dashboard in this key section. So I can copy this key, and with the Edge Impulse commands, I can do Edge Impulse daemon, which I have up here, and then I can add a key, and this will connect my device directly to the project. Call it Josh. And so now this device is connected to the PSoC 63 project that I have here. You can click on the link, and since I have the project open, I can go right to it. And then in the devices section, I can see that I have my device connected. And it tells you what kind of sensors that are allowable with Edge Impulse. In this case, the microphone or the inertial sensor, or even some of the environmental sensor you can take data with. If we go over to data acquisition, this view is where you can work with your data sets. You can split your data into training and test sets. That's very important for model design. You can explore the data to see how your features are generated. You can upload data sets as well. So let's say that you have files already on your computer from previous runs, either WAV files from that you've collected outside of Edge Impulse, or you want to upload a data set, like a known data set, let's say Coco for images, or the Google speech command set for speech commands and utterances, that can be done via this portal. Or ideally, you can take from device. So I'm going to do motion data today, and I'm going to just have the board sit here on the desk, and I'm going to take about 2 seconds worth of data from the inertial sensor. So I'll be sure to select it here, and I'll just start sampling. What Edge Impulse is now doing is through that CLI tool that's running on my machine, talking with the device on my desk and collecting accelerometer data. We do the 3-axis accelerometer, and we can then work with it and either split or crop the sample if it was an image, or even relabel it if we need to. We can also get it into the test set very simply by clicking here and then, again, doing another sample as well. You'll see some interaction on the CLI to prove that this is working through. I'm going to do into the training set a very simple up-down motion. So I'm going to take this and I'm going to start sampling. And so now I'm just bringing the board up and down in a motion as well. And we'll see what that data looks like. So you can see it's different from idle. And then what eventually we're going to do is collect a number of these. And I'll show you a project that already has this data collected. And then work on spectral features off of that and pass it to a convolutional network for classification. For a lot of these getting started tutorials, you only need, a few minutes of data, 15 minutes of data, so maybe like 3 minutes of data per class. We've seen projects that, want to see if a device is like floating in the water. Maybe they don't have GPS or anything, and then they want to characterize that motion between being in a car, or as Seshadri said, they want to characterize whether somebody has fallen down and hear the utterance of like help or ouch. And maybe you classify that as a priority event for a particular situation. All this kind of data you can collect with Edge Impulse. We do make it easy to get started with the project, even if you don't want to go through the steps to collect a lot of data. We have this project that's clonable. That is to say that you can copy its contents from what we would call public profile into your developer account. Let me show you how to find that. If you head over to edgeimpulse.com and go over to projects, and you can just type in Infineon. And these are projects that have been using the keyword Infineon or have been known to test out with Infineon products. A lot of other projects that use accelerometer data, microphone data, or any other kind of sensor can very much run on the Infineon boards. If it's a custom sensor that's not on the dev kit, we have some porting guides that show you how to connect any kind of sensor data into an inferencing. For example, we know that some Infineon products have been used for radar. Somebody has published a project for that as well. Today, I'm going to show you this motion recognition. This is one of our main getting started tutorials. In this case, we classify on data like moving the board in a snake-like fashion versus waving it, going up and down. And we'll talk about also what an anomaly score is. From this project, you can clone into your own repository, if you will, in Edge Impulse, and then it allows you to go and edit and add new data, things like that. I happen to have that project already cloned into my system. It takes about a minute to transfer from one ownership to the next. And you can see here, this project has about 15 minutes of data collected, split across training and test sets. So here's an example of the idle motion. Here's an example of an up-down motion, etc. The next step in your journey after you collected your data is to work on your impulse design. An impulse, again, is how you take data from what sensor you're going to take it from, what kind of processing you're going to do on the block, and then after you've done that processing, what kind of classification or neural network you're going to apply to it. A few features of each block here. This code, if you will, is actually running on device, right? So there's a representation in C in our GitHub repo that represents this code. It shows like how long you're going to take data for anomaly. And then if you do take data longer, let's say 10 seconds, how that window is going to shift over time and at what frequency you're taking it. You're going to either downsample or upsample that data. There are a number of different spectral blocks available in Edge Impulse. Today, we're just going to work very simply with spectrograms or spectrographs. For microphone or keyboard spotting, we have MFCC, MFE. And then if you have your own kind of custom IP, I've worked people with time of flight sensors and other things like that want to build different kinds of spectral features. That's you're able to bring in or customize these blocks to work on code that you may have of your own. For classification and anomaly detection blocks, again, you can select it here. You can also do regression and then other kind of classification depending on other hardware that you have. We chose the spectral features because that's pretty easy to recognize motion based upon you know, what we see for FFT and then Kespra and things like that. The block has the ability to auto-tune across the data set. And so what it does here is it looks across your whole data set and tries to help you pick out the best parameters. And really what we're extracting here is we have raw, either audio or IMU data or sometimes image data. And then we're going to try to pass out from it, you know, a certain kind of filter and a spectral graph that this data that you see here is actually being pumped into the model. We also try to give some sort of performance indication about how long it might run on a particular device. So here, maybe we say 4 seconds at 2K of RAM. You need to generate the features. And after you do feature generation, it builds what we call a dimensional reduction of this data set. And so through this process, and the documentation is online about, you know, what we do, I believe it's UMAP operations, you can kind of get groupings of data and you say, okay, I see that, you know, this kind of motion is being interpreted as up down. You know, this kind of motion is a wave. But this is our first chance to really, or one of our chances to start seeing if we potentially mislabeled data. Of interest here is this green in the sea of orange, right? Maybe this was misclassified. Okay, so we said these all look like snakes motion, right? Remember, snake motion is kind of on the ground, going back and forth for this particular board. Well, let's take a look at this one, this up-down motion. Does it look any different? Well, that particular window might have been a transition between somebody was doing an up-down motion and potentially weighted that way. The model, when you're training it, might get confused based upon that. So you may want to go and either work with that data, edit it out, or maybe that's an important use case in your model design that you hadn't thought about, right? And so you might want to make your model stronger against that and need to go collect more data where you might do a transition from an up-down to a snake, where you mistakenly classified that. I've seen projects that have thousands of different classifications. And so it's very helpful to go look at this view and start figuring out if this is if your data is done correctly. After you process these spectral features, you're going to be passing it into a model. We start off with the default classifier here. It's just a few dense layers. If you are familiar with ML design, you can go and add your own layers in a visual way and kind of drag and drop through this view. You also have the ability to go into what we call Keras mode and actually edit the Keras code behind it. The Keras code will get translated to TensorFlow Lite for microcontrollers and then eventually built into the project for the Infineon device. Again, in the way of total explainability, if you want to see the full training pipeline, you can click on Edit Block Locally. What that will do is deploy, give you a Docker container for which you can run the whole pipeline from getting the NumPy files of the spectrograph into the model and seeing how the training is actually run. Training takes only a few minutes to do for this kind of data set and this kind of model. Very much easily done on a free developer account. We profile both the float and the quantized model. We typically run the quantized model on device. This classifier does a very good job of detecting, you know, one movement from the other. You can see it had a few misses here in the training data set. We could go and explore this and say, all right, well, why did it potentially, we labeled this as up down, but it predicted that was a wave. If you need to go get stronger assurances for that, you can go again and work on your data set. Data is king for ML. We can't stress that enough. We also profile these targets in Edge Impulse. So here we have the 063 and 062 devices. And we try to give you a sense about, you know, how long is it going to take to do an inference? What's your peak RAM and flash usage, that kind of thing. Let's talk about anomaly detection. So in this model, remember, we only had a few classes. We had it where it was sitting on the desk, where I'm doing a snake motion and waving it and going up and down. What if you do something like, throwing it back and forth, okay, or you're dropping it very suddenly in that up-down motion? When you look at the spectrograph for those kind of motions, or even for keyword spotting, and somebody says a word that's not known, or even on the visual sense, we can get a sense about whether or not we've seen that data before. And so again, with kind of reducing the information down to a few dimensions, this data will start grouping. And then maybe one of these new motions will be outside of that group. Well, we can, there's an algorithm to see how far it's moved away from the cluster, k-means clustering. And that's an anomaly score. And so it's very important to look at it and say, all right, I'm classifying as up, down, or idle, but my anomaly score is really high. Maybe I don't trust that classification. In that case, what we suggest is kick off some storage to flash, right? And then send that data back up to Edge Impulse. We have APIs, or again, you can link to the CLI tool, and then build a new model with new classifications and go build up a stronger model as well. And that's what we call active learning, right? This kind of continuous process of making your model stronger over time, making it recognize more things. And this is something you can do by detecting anomalies, recording data, and getting it back into Edge Impulse. With the Eon tuner, today I only have just a few data sets in there. But what that feature allows you to do is to work through a bunch of models, starting with the base model that you have as that you have trained on, and it actually kicks off multiple jobs. So let's say we're going to test a model with, 3 dense layers, 4 dense layers, maybe different filters, maybe different DSP code, and allows one to search across a whole space. This is one of our enterprise features because we are kicking off multiple training loops as one and building out into the cloud a lot of jobs. This is very good for, let's say that you developed a model that maybe is like 85% accurate. And then you want to see, okay, what's it going to take to get to 90? Maybe I need to go change some layering, or maybe I need to increase my inferencing time, etc. Eon Tuner is the tool for that. In model testing, what we had done is looked at when we trained a model, the training set, but we have a whole set of data that the model has never seen before. And so it's very important to classify that and see if your model actually is performing on potentially tougher data sets. In this case, the model does okay. 99% accurate, I would say it's probably overfitting in reality. But again, more data, the better, right? And then especially, taking out the transitions and things like that. We have the ability to version projects as well, so that you can store off, the whole data set and the models that you're trained for, and you can also version DSP and kind of do A/B testing between models. Before deployment, I do want to show off a couple other projects that we have with the Infineon devices. So we have continuous motion recognition. We can go over to keyword spotting. These are, again, one of the clonable projects that you can immediately start with. In this particular data set, we have 31 minutes of data. You can filter around keywords here. We're Infineon, background noise, other spoken words, things like that. Remember these spectral blocks? In this case, we use the MFE. And this is the spectrograph that's passed essentially to the classifier. For those who are familiar with some of the ML architectures, this is a MobileNet V1 model that was transfer learned against it. And you can see that, hey, the accuracy does pretty good at recognizing certain keywords, but maybe some of the background noise is tougher to work against, right? And we can see that, some of the background sometimes gets incorrectly predicted between unknown and background. Maybe that's not a problem for your particular model, but it does a great job at predicting the actual keywords like Infineon and AIROC. And again, for model testing, we'll look at seeing at this data set as well. I wonder if model testing has done that. Yeah, and you can see with the testing data set that it performed a little less accurate when it's tested against something that it hadn't seen before. Again, data is king for your models. More the merrier. So let's actually deploy one of these projects onto a kit. So I'm going to go back to the project that I've cloned. This is a continuous motion recognition project. In the deployment options, we have a number of ways to get data or get the project onto your device. Here we have the fully built firmware. What this allows you to do, these two options, is it'll launch a job in Edge Impulse and actually give you a hex file from which you can program against the device. Then you can use the CLI tool to run it. Alternatively, you can deploy as a C++ library and take the source code, again, open source, with your model parameters, and then build it into a larger application. So the difference between these, where we have the picture of the boards, and the C++ library, is that the one with the picture of the boards gives you the binary. And this is a quick way to test on the device without ever having to write any code. Or you can take the C++ library and start developing yourself. One way to do and work with the C++ library is to use a Modest Toolbox. We do have a number of Modest Toolbox examples out there, and we're expanding that even as we speak. I'll show you where some of these exist for some of the other Infineon projects. You do need to choose your particular board support package. I'll show this device here. And here in machine learning, here's one of our continuous motion projects that we have. So I'll close this out. And then today I'll choose the BLE kit. So I'm going to choose the quantized Int8 model. We'll enable Eon compiler that allows us to get slightly better performance and less model size for the device. And I'll click off build. Building takes a minute or two. I have already built this project before. I'll show you how to program on device. I happen to have a Windows VM, and I am going to copy this file over. The file it produces is a zip file. I'll extract it and extract here. And then I'm going to use the Cypress programmer. This is the programmer kit for the Infineon products to put on the device. And so I have 089 there, 089 there. And then I need to associate my board with this virtual machine. So I will stop that, tell it to connect to the VM. And the scikit kit is recognized. So I'll connect, and then I'll program. So this is me live programming this keyword, sorry, not this keyword, this motion detection project onto the device. You also need to do this step to initially get started with Edge Impulse firmware. In that documentation page, we have that firmware available. This little Chrome window is bouncing. Hey, look, it built out. And we can see instructions as well, like install the scikit program and install the hex file. And we can get the build log from Edge Impulse. Let's see how we're doing. We're about 75% there for programming. All right, device programmed successfully, and it's starting to flash at me already on the screen. So I'm going to on the device. So I'm going to disconnect. I'm going to unassociate here. So Ashok, the AE who's on the panelist with me, and then Dimi, our embedded engineer, did a great job with the blur, programming up the kit E display to kind of say like, hey, we're running machine learning with the PSoC 6 Bluetooth, and we can actually run an inference on device. So the command for that is Edge Impulse run impulse. And here it's actually starting to take data for every 2 seconds. It's going to take some data and then tell me what the classification is for it. So I have it sitting here on my desk. So now I'm going to go do an up-down motion, and the classifier should say up-down with high confidence. I did a transition there. So again, it's going to maybe misclassify, but you can see the anomaly starts going up. I'm going to do a snake motion. Let's do this on my desk. So the snake is classifying pretty well. And then I'm going to do this kind of throwing back and forth. This is not something we took data for. And so as you see the anomaly score starting to bump up almost to 1.0. And the further it moves around from data that it's seen before, the worse that anomaly is, the bigger the anomaly will be. But you can see it's still starting to say, hey, that looks like an up-down motion, but the up-down motion typically has an anomaly score like 0.2 or something like that instead of 0.7. Another feature that we have with the firmware today, and the firmware that we have on the device actually outputs to BLE. So if you look at the screen on the device, it tells you, hey, there's some BLE code running. Let me share my phone and we'll show that off today. So I'm going to go here, share and connect to my computer. Great. And so there is a app from Infineon that we can do and click on it, download it from the App Store. I'll click on the Edge Impulse app. We have the SCAT device. In this case, it just happens to be an unknown service and characteristic, but I'm going to turn it on notify. And it will start telling me like the board's sitting here idle. Then I'll go ahead and start doing an up-down motion. It started a transition to a wave, and then it'll grab the up-down motion here as the next sample comes through. There we go. So you can see there's still some considerations for model design that we need to work through in this app, right? And again, it's all about your data and how you classify. Maybe you classify transitions as well and not use that to make a determination about what your bigger application will do. This code is available through Modest Toolbox and of course on the GitHub repos through Edge Impulse and Infineon. Last two slides here. If we come back, we do have Imagine I want to plug really quick. This is a online conference that's all about Edge AI. So Infineon and other of our Silicon partners will be there. This QR code is live. You can register today. It is on September 27th, starting at 9 a.m. Pacific time. And the link as well is edgeimpulse.com/imagine. And then Sheshadri has pointed out today, you can get started with this right away. These kits are available to purchase. Here's the 062 BLE kits, the one I demonstrated today, and with a free Edge Impulse account. You can immediately get started, clone some projects, or start collecting your own data from your particular device and custom sensors, or just use one of the dev kits to try things out. Thank you. Sheshadri, do we have any questions or comments or anything to add to this presentation?
There's a question or so that got answered by Ashok recently. We are open for questions that you guys might have. Thank you, Joshua, for the detailed steps.
Okay, so I have a few questions here that have come through. Firstly, how do I use different sensors that don't come with the dev kit?
So there's a couple of different ways. One with the dev kit, both the two dev kits that, and maybe Sheshadri, if you want to show up that slide with the other dev kit. You can use Edge Impulse. The firmware is out there, and it has porting guides to use your own custom sensor. There's ways to integrate that into the firmware and build it into Studio such that you can use the Edge Impulse data forwarder through like a serial command, or you can build it into your application and eventually just get your data into Edge Impulse as well. The dev kit provide multiple ways to access different pins. In this case, the one on the left-hand side that Sheshadri is showing has a number of sensors already built in. But then using the 063 BLE kit on the right, this proto one, might make it a little bit easier to work with some custom sensors. And again, Edge Impulse can take in a number of time series and vision-based sensors into Studio, so you can work with them to build models today. Sheshadri, I'm not sure if you have other sensors that you want to plug or talk about drivers, device drivers, things like that.
Yeah, in general, I mean, for the proto kit, especially, there's a documentation that's available that talks about how we have used an external sensor, not the same for the IMU sensor. That may or may not be the same one that we have on the board, but through I2C, you can plug into other sensors.
And then if I could share really quick, Ashok had done a really great, had done a great demonstration with using a custom sensor on a ball. These are actually one of the projects that you can clone again. And thanks to Ashok for working on this. This has been a great project as well, using the other sensor kit, and then it has also integrated an app as well. And the code will be available. We'll put it in the documentation pages so that people can easily access it.
Okay, and then we have one more here. How do I get profiling and performance data on device?
Great. That is a good question. So we have in the classifier, mine's still running actually. If I go back to here, multiple ways. So remember from Edge Impulse in the studio projects, we show off individual device performance. So I can go here and click off on different boards and try to make a prediction about what this model will take and how fast it'll inference both DSP, the DSP code and the inferencing time itself. So this matches pretty well. Again, we benchmark a lot of these models and then also make extrapolations to if you add a few layers, like how much that compute time that's going to take on device. So you can see that the classification actually runs really fast, just running those few dense layers, even sub-millisecond runs. But the DSP code takes a little bit more to run that FFT as well. Because we are taking a lot of data and then trying to consolidate it down to just a few key points. This is a very important aspect to machine learning. We're always making improvements to this tool to get better predictions, both in the cloud and then on device. If you need to see some of the structs as well, if we head over to Google, we can do Edge Impulse SDK. The documentation pages have information about those particular structs and then how you can use them in your application. So I can go here to this inferencing SDK and then look at this particular struct. And this is the result classification that you're seeing on the screen, the label and values, and then as well as some of the timing information that you need, like the DSP and how long it takes to run or how long the anomaly score takes to run. This is all what we've done with Infineon to port Edge Impulse SDK onto their devices. And this is true across all our officially supported devices.
Okay, and the last one I have here is where do I find the code for the BLE application?
Ashok, for the BLE application, or Shashadri?
Ashok has.
Yeah.
Yeah, go ahead.
Yeah, I'll be sharing the link on the chat window.
Great.
Okay, that's all of the questions. Thank you everybody for joining. If you'd like to rewatch the webinar, it will be available on demand. You can just use your registration link to go back in and rewatch anything. We'll be back soon with more from Infineon and Edge Impulse.
Thank you.
Thank you.